we all know, like in a 2D setting, if we have a image, and when we apply convolution, we have a local patch of the image on which we apply something called 2D kernel, which is the filter to get the features, right? So in case of 2D CNN models, the kernel is actually composed of weight parameters. Yeah. So these parameters, they kind of share the same pattern across. I mean, you use this kernel and go through each part of the image and start extracting the features. Here, what it does is like it try to calculate some kind of a similarity between the patch and this 2D kernel, and that's how the feature is obtained. So let's quickly go to what is graph convolution, the idea of graph convolution. Okay. So one thing that is that we clearly see is like data is not anymore in the form of like image, which is a regular grid structure, right? So here, it's if you take any node, the number of neighbors to that node may not be fixed, right? Like as in case of an image, you have 9 pixels around any given pixel, right? Of course, not considering the edge of the image. Okay. So if you take another node, then you will have only 3 nodes as the neighbors. So this keeps changing based on which node we are looking at. Okay. And in case of graph convolution, what they do is like, let's say there are features for each node. Okay. So what they do is they do some kind of aggregation operation at each node. Okay. In this case, they are doing average. They can also do max. So what they are doing is they are taking the node itself, its features, and the features of all its neighbors. And then that's how they create the average. And the average value they feed into a neural network, in this case, a fully connected network, and they get features. And these features are for this node. Similarly, for another node, they take its own features and also features of its neighbors, okay, and then aggregate them and pass through a network and get features for that particular node. So this is what keeps happening for each part of the node. And you know, like by doing this, each node will be learning some information about its neighbors and also. Okay, and this can happen through multiple layers. Okay, so this one pass of idea is like one graph convolution layer. Okay, and then you have features, you then aggregate them, pass to another network. Okay, so you keep doing that so that you are getting more features for each of the node. So this was the idea behind graph convolution. And now we have to look into what happens in case of a point cloud. So if we compare with the 2D, right now, a small portion, okay, if you pick one point and pick few neighbors around that point, that portion will become more like that image patch what we talked about. So here we call that as a local region. And there we have 2D kernel, but here we have, I mean, the paper defines for a 3D kernel, okay, and they apply that kernel to this neighborhood and extract the features for the center point. So input to the 3D graph convolution network is the point cloud, which has n points. I mean, in most cases, like most models start with a 1024 points. The input is the entire point cloud, the entire rabbit hole. And each point has the x, y, and z coordinates. Okay, so there are little bit, I mean, this paper has named the notations in a different way. Okay, usually if we have to refer for each point, we might use I, but they are using a small n. Here the capital N refers to, the uppercase N refers to 1024 points. Okay, so let's go into detail and see what is this the neighborhood, what is equivalent to an image patch, right? So what is this, and then what is a 3D GCN kernel? And the task at hand is like classification. Okay, so if we feed in the input through the network, we should be able to get C scores, where C is the number of object categories. And if you have input point cloud, we should be able to say to which object category it belongs. And also, in case of segmentation, for each individual point, we'll get a score, and that score will define like to which class that particular point belongs, because parts of the entire objects are labeled, and that's how semantic part segmentation is. So yeah, this was the neighborhood portion which I was mentioning about. Not to confuse, looking at this sphere shape thing, not to confuse that it is some kind of ball query around the point Pn. The authors are not using ball query, so there is no radius component. What they are doing is to get the neighborhood, they are using k nearest neighbor. So if we go back to this entire input point cloud, if they pick a point here, they will just compute the distance to all other points in the point cloud. So they have a huge metric. Since the input point cloud has 1024 points, they have a 1024 cross 1024 matrix, which keeps the distance of each point from all other points. Okay. Yeah. So now looking at the neighborhood, let's say we are looking at the neighborhood of point Pn, whose coordinates are x, y, and zn, and then we can see 5 neighbors. Okay. This 5 neighbors constitutes the receptive field points. Okay. So, and each neighbor has its own features. Even the point we are considering right now, it also has its own features. Okay. If you have a point, let's say there is a function using the coordinates, it kind of maps it to a higher dimensional feature vector. And they define something called directional vectors. Okay. If you take each point, they subtract that from its neighbors. That way they get a directional vector. Okay. In the initial case, like all points are just the XYZ coordinates, right? So the directional vectors are also kind of XYZ coordinates. But later these can be longer feature vectors. Okay. So, and yeah. So this is the part where they say what is the receptive field. This is all about the collection of points, including that specific point around which we are looking at the neighborhood. So this is the definition for receptive field. Yeah. And yeah, I told about each of them has features. So that is another set. Now looking at the kernel portion. Okay. And this is the 3D graph convolution kernel, which they suggest. And here also they start with a center part of the kernel, which is always 000. And then they go about 3 points. I mean, nothing to compare with these points. This is just specific to the kernel. And they call those as support. So s equal to 3, we have 3 items supporting the center kernel. And each of these are called kernel points, including. So that in this case, when support is 3, there are 4 kernel points overall. Okay. And if support is 1, so there will be only 1 item, and there will be total 2 kernel points, KC, as well as that. Even for the kernel items, each kernel point has its own weight. Okay. And again, here also they compute the direction by taking out KC, but anyway, KC is 0. So yeah. So what we say is, for the local region, okay, they have the features, they have the direction, and of course the original coordinates. Okay. And for the 3D kernel, they have the number of supports, each having its weight and also direction. So now we'll go further from here. So this is kind of a basic setup. Yeah. Again, weights can go to higher dimensions too. Okay. Yeah. Now we'll get to the 3D graph convolution part. So what they do is, for here P1, P2, they are the points from the neighborhood, and K1, K2 are the support in the kernel. They are the kernel points. So for each kernel point, okay, and with each actual point in the neighborhood, they compute something called similarity. Okay. So this is the equation. And to compute this, they use those directional vectors from the neighborhood, and they use the directional vector of the kernel. Okay. And they compute this part. So here we can see they have a point here, and then they compute with this kernel. They have some higher value. Okay, this is to say like this is a cosine similarity, right? So this is to say like how similar, they are trying to extract that similarity pattern from using this kernel on this data. Okay, and then you can see like, okay, the same kernel but at different points. Maybe from here you can see they are like almost opposite oriented, right? So seems like they are not that similar, and the value is negative. And then with a different kernel, okay, on the first point, again, they are more of at 140-degree angle. So it seems like the similarity is negative. Yet again, here it is much closer, so a positive value. So what they did is they computed the similarity by taking every pair that is there in the neighborhood point and the number of supports in the kernel. Okay. Here, this operation here, that becomes the inner product operation, the dot product. Okay. And now the convolution, this equation represents the actual convolution which is happening around. Okay. So we know that each point Pn has its features. Okay. And of course, the central piece of the kernel Kc also has its weight. So they do this dot product, and of course, by doing this, they get features. And then these features are more relevant to the center piece, right? Like the center point Pn. Okay, now this portion we need to understand, since they already computed the similarity between those kernel points and the actual points. Now they will go for picking the point with a maximum similarity. So in this case, 100 is max. So for kernel 1, that is what the max value they picked. In case of kernel 2, what is max? So that is what they picked. Okay. And through this convolution, through this dot product, they had got some values for 60. So they add them up and they finally get a value for, I mean, the input here is the receptive field of the point Pn. And of course, we have the kernel. And now they got this value. So this is the convolution operation, what they have suggested. And coming to their architecture, okay, they have laid down these layers. There are convolution layers, a couple of convolution layers followed by the pooling layers. Okay, and the data set they used was ModelNet 40 for classification, and they achieved accuracy of 92.1%. Of course, it's not the state of art, but still comparable with many of the models here. Okay. And here in this, what we can see is they are starting with 1024 points, okay, and they will convolve and get some features, okay. We still have the number of input points. They get these 32 features, okay, and then they use the whole thing, convolve further, and the number of features are increasing. So when we spoke about the graph convolution idea, there also, like for a node, they calculated features, and then for all the nodes, and then in the next call of the convolution, again they calculate features, so their features are increasing. Okay, yeah. At some point, the graph convolution also suggests like it's more effective if it's used in 2 or 3 layers only. So at this stage, they have good information in these features. Now they go for a max pooling, and from 1024 they pick 256 points randomly. Okay, and again the process continues. They have a pass it through the convolution, and further they do again max pooling. So what we observe, one different thing compared to the actual point net is there, we have 1024 features also for 1024 points. But what we are seeing is the number of points decreasing. At this stage, we have only 64 points, which are critical. And, we have those features. So they do a max pooling to get the global features, which are used for classification. Okay. This is the architecture for classification. Now, what we'll do is we'll go a little bit detail into what exactly is happening in each of the kernel, how they are doing it. So let's pick the first block, which has the first con layer in second, and then the max pool layer. So in the first con layer, what they do is they go and get neighbors of each point. We know a point cloud. We saw an example of the rabbit curve. And each point, they go and get some neighbors. Since they are using k nearest neighbor approach to get the neighbors, they go and they set k value of 25 and pick 25 neighboring points around each of the points in the data set. And from them, they will subtract, from the neighbors, they will subtract each of the points. That way they get the directional vectors, okay? And they normalize that. That is how they get the neighbor direction norm, okay? And for support, what they do is they randomly, they uniformly initialize the values between a few range, and then, they compute a direction vector there and normalize that also, okay? So, and then they do a dot product of that. So by doing that, what happens, each node has those features, okay? And then what they will do, from those 25 neighbors of each point, they will do max pooling to get, the best features possible for a given node, okay? And we spoke about support, okay? Support was like multiple kernel points, right, in the 3D kernel. So if there is only one support, no need to sum it, right? If there are multiple supports, in those cases, there was a different vector of features for each support. So they just add them up, okay? So these are 6 steps which they do in the first con, which is like, they have designed it separately. Remaining consequent kernels. So what I was suggesting is, the dot product in the first layer is only the cosine similarity, okay? Yeah, so in case of multiple, they add all of those. In case of single, it's just the value. And in subsequent convolution layers, the first 4 steps, they remain same, okay? And now the actual weights they have, which needs to be learned. So the features which they got here, they just, this is again convolution operation, and at this stage, they get much more features. And now they have those features as center features and the neighbor features. So they take the neighbor features from that, and they just do element-wise multiplication with what they got here. So at this stage, like each node has a huge set of features, and take the max for each of the neighbors, and then of course add them if there are more suppose. And they will again fuse back the neighbor features which they have taken. They will again fuse back with the center features. That's how each node has its own features fused along with the features from the neighborhood. Okay, so with this we have the first two parts from this block. Now let's look how max pooling happens. Yeah, as I mentioned, in the first layer it's only just this cosine similarity being processed, but after the first layer we do have features here. So those are used in the cross product for subsequent layers. Yeah, we saw this equation already. Yeah, each convolution layer takes point cloud as input and the features. Of course, we have for that layer we have a kernel, right, and that gives us a point cloud. In this case, it's the same point cloud. That's what we said. Like we have 1024, 1024. So it gives out the same point cloud, unless we go for a max pooling layer. So in convolution, the input and the output point cloud are same. Only the features change, and we can see the number of columns are increasing, right? So it's kind of a more of a channel rising actually. Going with a max pooling operation, okay, like at that after two layers of convolution, the first and the second convolution, we have each point with a huge vector of its features, okay, and those can be represented here, okay. Each point it has its feature, and also like its neighbor, they also have its own feature. So all of them are stacked up here in the form of a row. So for each column, they go and choose a max. That's why they call this channel-wise max pooling. Okay, here you might wonder, okay, from here they do max pooling, but why there are same number of points? The points won't change, only the features are max pooled. So the number of points remains same, okay? This is just an aggregation operation. Now, from whatever they had here, they do a downsampling, okay? We had capital N number of input points, right? They apply a pooling rate, okay? Say, for example, in this, they have taken a constant pooling rate of 4. So if you had 1024 points with 4 pooling rate, the number of points would become 256. That's how they downsample. So that's how they pick this. But doing this downsampling, they are using a random approach. So they randomly select 256 points, okay? And this is how they got this. And in pooling layer, you have an input point cloud and a reduced output point cloud. And the features also had got changed, right? They got aggregated in this. Yeah. So both for features as well as the output, the pooling rate was applied. Yeah. The point cloud, it will still remain as a the same dimension, but features dimension. I mean, after each block of it can change. For a given block, it will be still same. Okay. Yeah. So these were the steps. Even in this get neighbors, take max of those. That's what they are taking max of max features of those, and then randomly sample using the pooling rate to get the final features and points. That was like part. I mean, that was part of the whole block. The similar blocks can be used even in segmentation, convolution pooling, convolution pooling. Okay, so for segmentation, they are using a ShapeNet part dataset, which has a 1680, 881 models with 16 categories, 16 different types of objects, and including the subcategories. For example, for a given aeroplane, the tail, the wing, the engine, all those subcategories. Totally, there are 50 categories. Here also, they are not breaching any state of the art, but they have a comparable result. Both even in classification and segmentation, they are getting comparable results. The surprising thing was they didn't breach for any class also they didn't breach. So all these values are less than the state of the art values. Okay. So in this architecture, the same thing again, like the number of features, they keep increasing, and then the number of points keep decreasing. They take those features and concatenate all of them together. Okay. So you may ask, like, well, here 1024 points are there. In the next stage, there are only 256. So which one they are concatenating with which? So what they will do is they do a one-hot encoding based on the distance of the point. If they pick one point here and the other point here, if that distance is 0, that meant it is the same point, right? So those feature vectors, they will take the feature vector of that point from this tag and concatenate it. the other. Okay. And then this very large feature vector is used for classifying each of the points into these subcategories. So this is the architecture for the part segmentation. Yeah, now, yeah, we wondered they didn't have great results for classification or even for segmentation. But now this is where the good results of the paper are. Okay. So what they do is they randomly shift the objects in all directions and feed that as input, and they are able to their results are much stable. Okay. So shifting by distance of 1, 5, 10, or even up 100, their results are very much stable and very much better than KPCon. Okay, kernel convolution. Yeah, and especially for for PointNet, we can see how the scale, the shifting would drop the accuracy. And then they also do it with the scaling. They scale the object, they scale the object downward, and they also scale the object upward. Okay, so one is the actual object as it is. So for most of the models, it keeps decreasing by scaling downward, also by scaling upward. However, their model is doing really good. Okay, in this case, we can see like DGCNN is also kind of doing comparatively well because they do have their objects scaled while training. Okay, so this was another good result. The third one was how about rotation? So they rotate along the upward direction, and still 3D has really good results. Okay, DGCNN also had rotation as input, but if they get an object with a different variation of rotation, their performance goes down. Okay. And these are a few of the results from the segmentation part. They are comparing with KPCon and PointNet++. Here you can see by shift, the PointNet++ would just label it with one label. Okay, whereas here we can still see the label very much clear for different parts of the object. And this is the ground truth. This was the very important result what they got. The number of parameters have reduced way. I mean, KPCon was one which was having even better results, even in case of classification and segmentation. But you can see the number of parameters they are using is way too much. Okay, with such less number of parameters, 3DGCN is getting very good results. So this was one of the main factors. And also we understood why the number of parameters got decreased, right? Like, after each block, we saw the max pooling reduced the number of points. Okay, that's one main reason why the parameters decreased. Yeah, and yeah, these are a few snaps from the segmentation part. After each layer, how they have captured the responses. Here we can see like the responses have shifted to more of a part level, in a yeah. This is to show like what dominating responses would be there, and yeah, this is it. Yeah. Any questions?
Hey, Sean.
Hi.
Can you go back to the slide where you showed the equations, or where you showed the number of steps required in GCN?
This one?
Yeah, this one. So over here, if you see, you have written 4 is multiplied by the weights, right?
Yeah.
I thought over here, instead of 4, you have the previous layer that gets the feature maps from previous layers that get multiplied to the weights plus B.
Yeah, you are right. Yeah, you are right about that.
Yeah.
Yes. I mean, whichever features we got here, that would go here.
Yeah, because this equation would bring the right-hand side of the DM and KS to this, which is not what we are doing, I think.
Yeah.
Okay. And so in GCNs, you usually have an undirected graph, but it is not closed. But,
yeah.
And in 3D GCN, you have this graph, which is actually a big closed graph, correct? Because you have the information to all its neighbors.
Yes.
So do you think it is fair to say this is actually a graph convolution that is occurring over here?
Are you asking like if there are multiple components in the graph, like different? Let's say this is one part of the graph, and then there were few other nodes. And are you talking about disconnected graphs? I didn't catch your question.
Okay, so in GCN, you actually do not have edges, or you do not have information between a few nodes. You do not have so for in your example, if you take the nodes on the right hand most sides, they are not connected to each other. Oh, I don't know, you skipped some slides on.
No. So in case of point cloud?
No, I was just talking about the graph that was on your slide.
Okay, let me go back to that. Okay, yeah, we have a graph here.
Yeah, and so if you see the nodes on the right hand side on the left hand side of the green node,
okay,
they are not connected to each other.
Yeah, you mean to say this is not connected to this?
Yeah, this is not connected to this. So this is what I meant when I said this is not a closed graph. But
this is not a complete graph.
Or not a complete graph, but over there in 3D GCN, your graph is always complete because of the way you are querying your nearest distance. The KNN, it's kind of assuming that you have information between all the neighbors, and it's picking up the 25 graph, 25 points or the 5 points from it.
Okay.
So do you think it is fair to say this is actually a graph convolution that is occurring over here? And also in graph convolution, you know that
okay. In both cases, they are only considering the neighborhood. That is for computational purpose why we have a 1024 cross 1024 matrix, which represents the distance between every node with every other node. Okay. But even there also, we just take the neighbors and we do computation based on those neighbors. Here also, if one node is picked, okay, its immediate neighbors are taken into consideration. Let's say if there was another point here, right, and that was connected to this, this has no role in this, at least in the beginning, right? Like, because its features are only communicated to this, okay? So maybe in the next layer, right, the features, I mean, this node would have the features of itself along with its neighbors, then this node would come into picture, and that would be communicated in the next layer, okay? So it's more like, kind of learning features through neighbors. But the original paper also suggests like if you keep on going, putting multiple layers, right? So what will happen is like all these features kind of start becoming stabilized, or like there won't be much meaning or much learning to do. Okay.
And the last question was, if you see the selling point of their paper is really reducing the number of points after a few convolutions in the downsampling step of the max pooling.
Yeah.
Can you tell me if this sampling is random or is it learned?
This is not learned. They just randomly pick points from this.
So in each forward pass, the points would keep on changing.
Yes.
So okay. So do you think this is like a area where there is like a scope to improve it, or do you think the random sampling actually helps in this case?
Because for one object, we might think of like, okay, for this object, it is going and picking, maybe not so, I mean, among these points, maybe some points are not so important, but they got picked because of the randomness. But for a different object, right, that would make sense. So there will be some randomness to, involved in how we are sampling these points. Okay, one way to figure out is like apply farthest point sampling and see like if that would change anything. But still, even if we apply farthest point sampling, we are not doing it by learning procedure, right? We are just applying the processing step here, like just picking the point. Okay. But if there are ideas where sampling could be learned, I think that's what happens in SampleNet, right? Like they sample out by learning through the network. Okay. Maybe putting those components would help learn these points.
Okay. Right. Thank you, Sean.
You're welcome.
Hey, Shivan, I have a question. I don't know if you know this, but when they retrained PointNet and PointNet++, and they essentially were testing the different scales for the points, did they
Okay.
adjust the ball query size like appropriately? Because I think that could be like a reason that it wouldn't work.
In 3D GCN, they are not using ball query at all. Okay.
I'm just talking about .NET and .NET++.
Okay. Yeah. There are no details about like how they train, particularly like what. I would go by like they would have used as it is. They didn't change any radius.
Right.
If they do so, yeah, right. Like.
Yeah, because my thoughts are like if they're going to scale up or scale down basically the size of the point clouds, but they keep the ball query fixed, like of course it's not going to work. So
Yeah, it's not
kind of a weird test.
Yeah. Oh, yeah, that could be one reason why the things are going down here, right? Yeah, that. Yeah, we need to explore that part.
Well, so I think this is the shifted slide, but I was talking more about the scaled slide. Yeah, this one.
Okay. Yes.
I don't know, just a thought.
Yeah, thank you very much. Yeah, it's a very important question. Okay. Any more questions?
Any other questions? So Shivanand, you mentioned about rotation stuff. Was it so? Is it based on the augmentations that they do, or they are in general rotation friendly? You had a code.
They just do suggest this upward direction rotation. I'm not sure like what is.
So I guess the question is when they augment, they do augmentation on rotation also, right?
Yeah.
So that means their database would have rotated versions. They're learning.
Yeah.
So how can they just kind of show robustness against rotation if they just augment their data with rotations?
Yeah, but what they are saying, those rotations are kind of fixed, and they are not doing too many rotations. They just do one rotation, right? Sure. That's what they suggest. Even BGCNN, which did that augmentation rotation on different variations, they also had a lower performance in this case.
Okay, so thanks for the nice talk, Shivanand. Any other questions, guys? Okay, thank you again, Shivanand. And we look forward to see when we have the next one, and you'll see an email from me. Have a great rest of the day, guys. See you.
Thanks. Thank you.
Thank you, Shivanand.
Thank you. I think I missed to take the screenshot of nothing. Sorry about that.